So, stretching and compressing sine waves. So yesterday, there you go, we got A. Yesterday we focused on where we had our sine waves, and we were moving them up and down, or left to right. So those are transformations. What we're going to focus on today is actually stretching these waves, and then adding those transformations after. So, by now you guys should be very familiar with the original sine wave. It looks like this. Okay? So we have 0, 0, 91, 180, 0, 270, negative 1, 360, 0. Those 5 major points. And we can continue that pattern backwards because we are geniuses. Okay? That we are. Okay, so this is our original sine wave. What this represents, okay, and our new variable is the A variable, so a number in front of the actual sign. Now, if you guys remember back to parabolas, an A will either flip, stretch, or compress. Okay, and we are going to flip this in a minute after. But we're going to focus on stretching and compressing. Now, normally, if there's nothing there, so the equation says y equals sine x, we make the assumption that the A value is 1. The A value is also the amplitude. Okay? For instance, take a look at this. From the equation of the axis to the highest and the lowest point, the distance is 1. That is also the exact value of our A. Okay? So now, that formula we had before, we add and subtract the max and min and divide by 2, we can now look at the formula and be able to tell what the amplitude is just by recognizing the A value of something. So, our next value here is 3. What we're going to be doing with this A value of 3 is we're going to multiply it. So A will be multiplied by all of our Y values of the original equation. Okay? So what we mean by that is, first of all, what's the Y value at this point here? 0. What is 0 times 3? 0. So that point stays identical. Okay? This only works if we haven't transformed it up or down or left and right left yet. Okay? From there, what about our 1 value? When I multiply that by 3, what do I get? So my next value is up here at 3. So already we're seeing a big change in the wave. Okay? Our next point is 0. 3 times 0? Oh no, it's good. Okay? So we go back down to 0, and then our negative 1 times 3. Negative 3, exactly. 0 is going to come back up. So as you guys have noticed, this A value, oh, I did that already, has stretched this. It's pulled it much farther up and down. And that's because our A value, just like with our parabolas, was greater than 1 in this case. So they've stretched this parabola. We'll finish it off. 450s up here at 3. Okay? And then again, you can continue that pattern back to the left. I actually missed this one. That's negative 3 down. Okay? 0, 3, 0, negative 3. So we'll try to connect this. Okay? So here's our wave. It's been stretched. That point should actually be here. Okay. Now that we've done that, we're going to talk about an A value that is smaller than what? So this A value, it's smaller than 1, but it's also greater than 0. We're going to talk about why it needs to be greater than 0 also. We'll do this one in green. Okay? This value is the exact same idea. Our zeros will still be at the same point, because our A value, even though it's a third, when we multiply a third by 0, we're still at that exact same Y value. Okay? So our zeros end up being the exact same. The big changes come in our Y value. So, again, we started at 1. What is 1 times a third? 0.333, or a third. Now, in this graph, it happens to go up by 0.333.
Good gracious.
Okay? So, it doesn't go as high as the original 1. It only goes to a third. 0 times a third is still 0. Negative 1 times a third is going to be negative a third. 0 again, and then positive a third. So if you notice, this graph, the green one, has been compressed from our original one that is in color black. Okay? This is only a third as high. The waves only go up a third as high as before. opposed to when we multiplied it by 3, where it goes up 3 times as high. Continue that pattern, and we have the whole wave. Okay? So far, a relatively simple idea. The only other one we haven't talked about is a negative value. So let's set that up. And we're going to give it a negative value of 2. Yeah, that'll be a good one. So we'll do that in blue. Negative 2 for our a value, sine x. Now, you can use the exact same process to do this. Recognize that a negative value is going to flip all of our original values. So if we're looking at the black wave, okay, a negative valued wave would do the complete opposite of what it does. Okay, it's been flipped upside down. But in this case, it's also been stretched by a factor of 2. So we can use the exact same method where we multiply the y values by our new amplitude or our new a value. What would negative 2 times 0 be? 0. We are still at 0. Made no changes from there. What would positive 1 times negative 2 be?
2.
Negative 2. Okay? So in other words, we come down towards negative 2. And that shows that we're in an opposite direction as we were before. 0 times negative 2 is still 0. What is negative 1 times negative 2? Positive 2. Great. So again, and it's changed from before, our new values are going the opposite direction of our original one in black. And you guys can continue that pattern. Again, it makes a pretty neat picture. Okay? And our blue one would be the last one here. So, oops, that's not what I'm looking for. If we take a look at this, a couple points that we need to know. Our A is now our new amplitude. If A is greater than 1, it's going to stretch from the original wave, so it'll become much longer. If it's between 0 and 1, it will be compressed, so the waves will not go, or the peaks and minimums will not be as high. And finally, if it's negative, it goes in the opposite direction. It flips what it originally was.